In this video, we're going to be taking a look at a method called partial fractions. Now, partial fractions are used to break down rational expressions with more than one factor in the denominator. Now, the factors in the denominator are polynomial because, of course, a rational expression is the ratio of two polynomials. So we have a polynomial expression on top, which could just be a constant, and we have a polynomial expression in the denominator. We're going to be using the fundamental theorem of algebra to break down the denominator polynomial into the product of linear factors and irreducible quadratic factors. Now, by irreducible, we mean that the quadratic factor won't factor further, like x squared plus 5 or x squared plus 2x plus 17. Those don't factor anymore, so they're called irreducible. Now, why would we want to do this? Well, if you look at something like this right here, in algebra, we generally started with a simpler fraction on the left, and then we got common denominators, and we combined them together to get one combined fraction on the right. Now, when we're in calculus 2, however, we're concerned right now with techniques of integration, which means if we want to integrate the expression up here, and we start with the one on the right, the problem is I don't know how to integrate the one on the right. This isn't u substitution because the du, if I let u be the denominator, the du would be 2x plus 1, and I don't have that or a multiple of that in the numerator. So it would be difficult for me to integrate what I have right now on the right side. The method of partial fractions then works in reverse to what we did in college algebra. Instead of getting it in one combined form, we take something in a combined form and we use the fundamental theorem of algebra to factor the denominator fully and then split what was one combined fraction into the sum or difference of two or more simpler fractions. And by simpler, we mean the denominators of the fractions on the left have a simple denominator of one factor or a factor raised to a power. And then we can, instead of integrating this expression on the right, we can integrate the expression on the left. Now, we know that when we have addition or subtraction, we can split the integral up. And this then becomes the sum of two different integrals. And these would be simple to compute using u substitution with u being the denominator. And that would give us 1 over u, which is the natural log of the absolute value of u. So this is kind of where we're going in this particular section. We want to take some rational expression, the ratio of two polynomials. We want to use the fundamental theorem of algebra to completely factor the denominator. And then we want to split it apart into simpler fractions, the sum or difference of simpler fractions, where each of the simpler fractions has a single factor as the denominator. At most, that factor raised to a power. Now, what are we going to have to find? Well, we're going to have to find these numbers that go in the numerator. That's going to be our unknowns. We'll know how to factor the denominator and break it apart, but we're going to have to figure out how many sums and differences of simpler fractions there are, and then we're going to have to compute what the numerators of those should be so that we can integrate. Let's go ahead and take a look then at some of the material in this section. I'm going to share my screen with you so that you can see more easily what I'm looking at. You should now be looking at my lecture notes for this section. This method of breaking down this rational expression into something that is the sum and difference of simpler fractions is called partial fraction decomposition. It's like you're decomposing a more complicated rational expression. It's also sometimes called rationalizing functions. A rational expression is a function. It's a rational equation. And so this is sometimes called rationalizing functions. I tend to call it partial fraction decomposition, or just partial fractions for short. Now, there are 4 basic types of rational quotients that we will consider. Now, what are these 4 basic types? The 4 basic types that we're going to be looking at, what we're really talking about is the denominator itself. the denominator of this rational expression, what are the four different types? Distinct linear factors only. And again, I'm only focusing on the denominator, not the numerator. When I look at the denominator, I have factor x minus 3 and factor x minus 4. They're distinct, meaning different, right? They're not the same thing. They're unique. And they only show up one time. So this is one type of rational expression we'll be looking at. And really, I should have only degree 1 in the numerator if we're going to do partial fractions, which we'll see in a minute, that we need a proper fraction to do the method of partial fractions. Type 2, we have at least one set of repeated linear factors. Now remember, a linear factor is x raised to the first power. So x minus 3 and x minus 4 are both linear. In fact, they have the form mx plus b, which is a line. That's why we call them linear. Now, what does it mean to have a repeated linear factor? Well, you have a linear factor like x minus 3, but it's raised to a power. In other words, it's there more than one time. In this case, it's there twice. So we have two different types. One, the denominator is all linear factors and none of them repeat. Two, they're all linear factors, but they repeat. At least one of them repeats, is there more than one time. Or third type, we have at least one distinct irreducible quadratic factor. In other words, in the denominator of the rational expression, we have a quadratic that does not factor further. Now, it could be something simple like x squared plus 3, or it could be something more complicated like x squared minus 5x plus 15, which doesn't factor any further. So it could be 2 terms, it could be 3 terms, but it doesn't factor anymore. So we call that irreducible, and distinct meaning different from the other factors around it. And we could, of course, have a combination of an irreducible quadratic with a linear factor. Again, notice I'm only paying attention to the denominator. That's the part that we start with in the method of partial fractions. The fourth type is that we do have this irreducible quadratic factor, but it also repeats. It shows up more than once. So in this case, we've got the irreducible quadratic factor x squared plus 2, which doesn't factor, and it's raised to the second power, which means it repeats. So these are the basic 4 types that we're going to talk about how to decompose. And by decompose, we mean rewrite this more complicated expression as the sum and difference of simpler fractions with single factors or a single factor to a power in the denominator. That's what we mean by decompose. Once we do that, then we'll have to learn a method of finding what goes in the numerator so that we can rewrite these more complicated expressions into simpler sums and differences of simpler rational expressions. Now, there are 3 basic approaches after we've decomposed it into the sum and difference of simpler rational expressions. There are 3 basic approaches to breaking them down and finding what goes in the numerator. They're called the Heaviside Method, named for Oliver Heaviside, who developed the method. The what I call choose wisely method, which is my favorite method. And then the method of equating coefficients, which is really sort of where both of the first 2 got their start. So the method of equating coefficients is really the theoretical method. It always works. It never fails. Choose wisely also never fails. It will work in all cases. The Heaviside method will not. The Heaviside method primarily works on linear factors. But since most of our problems have linear factors, this is actually an advantage because it's a relatively easy, short method to use. So we'll cover all 3 methods. You are welcome to use whichever method appeals to you the most. Again, our ultimate goal, take some complicated rational expression that's in proper form, degree of the numerator less than the degree of the denominator, and rewrite it as the sum and difference of simpler rational expressions where the denominators consist of a single factor or a single factor raised to a power. Then we can apply the techniques of integration to the expanded representation of the original rational expression. And hopefully that expansion will be simpler to integrate. Now, when we use partial fractions, we do want to start with an integrand consisting of some rational function, which again is the ratio of two polynomials, right? So you've got real coefficients and whole number powers on the variable x, probably, all right? You want to start with a proper fraction. Now, I did have an example earlier that was not technically proper because the degree of the numerator was 2 and the degree of the denominator was 2. So what do you do when the degree of the numerator and denominator are the same? Well, if the degree of the numerator is either equal to the degree of the denominator or greater than that, you're going to have to use long division. You're going to have to use long division to write the original rational expression into a quotient plus the remainder divided by the divisor. Now, the remainder divided by the divisor will, of course, be a proper fraction. And then we can do the method of proper fractions on the remainder divided by the divisor. If it's a proper fraction, then the degree of the numerator is going to be less than the degree of the denominator. So let me give you an example of what I'm talking about here. Let's say that you had something like, oh, I don't know, x to the 5th plus x to the 4th minus 3 over x squared plus 5x plus 6, something like that, right? This is definitely not proper. Why? The degree of the numerator is 5 and the degree of the denominator is 2. So what would I do? Long division. So I would do long division, taking the expression in the numerator and dividing by the expression in the denominator. And by that, I do literally mean long division. So you come over here. Hopefully you learned this in algebra. If you did not, then you're going to have some work to do to learn some things that you should have learned. Remember to fill in the empty missing terms with zeros. And then you're going to do long division. It follows the same process as long division with numbers. Basically, you estimate, you multiply, you subtract, and then you bring down the next terms. And then you repeat the process. So when I do this, I'm going to get a quotient up here. Now that quotient, if I'm trying to integrate this, I will then integrate the quotient. And then I have to do the method of partial fractions on whatever the remainder is. So let's say that I get something up here as an answer. And then I have a remainder, which never got divided by the x squared plus 5x plus 6. Remember, you stop the method of long division when the degree of what's left is less than the degree of the divisor. So that would be something that's degree 1 or possibly degree 0. So it would be a constant or a linear factor on top. So we would use the method of partial fractions on this part and integrate this part directly. After doing partial fractions, we'd be able to integrate that part. So these can be a little bit longer. They're not as difficult, I don't believe, as trig integrals or trig substitution techniques, but they are somewhat longer. If it's a proper fraction to start with, meaning the degree of the numerator is less than the degree of the denominator, then we'll jump right into doing the method of proper partial fractions. So now what we want to take a look at is the next things that are involved in doing this method of partial fractions. Okay? Why do partial fractions work? What's the theory behind partial fractions? Well, we're going to start with a rational expression, which of course is the ratio of two polynomials, p of x and q of x. Now we had a p of x and a q of x up here. This was not a proper rational expression because the degree of the numerator was greater than the degree of the denominator. But again, we're calling the numerator p of x and the denominator q of x. So we're mostly focused on q of x, which is the denominator part. Now, how does this work? Let's make an assumption that it is a proper fraction. If it wasn't, we've already done the long division. We've split it into the quotient plus remainder divided by divisor. And now we're focused on the remainder divided by the divisor part. which is definitely a proper fraction. So the degree of P of X is smaller than the degree of Q of X, all right? Making it a proper fraction. Then we want to apply the fundamental theorem of algebra to this in order to completely factor the denominator. Now, what does the fundamental theorem of algebra say? You should have learned it, but you probably don't remember it, so I'm going to remind you what it is. It basically says, if you have something that's polynomial in nature, you can write it as the product of linear and irreducible quadratic factors. In other words, every polynomial factors is the product of linear factors, things with x to the first, and things that are quadratic, x to the second, that don't factor further. In other words, I don't care what particular polynomial you start with, even if you start with something that looks like x to the fifth minus 13x to the fourth minus x squared plus 2. However this factors, and it must factor somehow, it's got to be the product of linear factors and quadratic factors that don't factor further. You've got to be able to break it down. That's the fundamental theorem of algebra. And we're going to use that in order to represent this original rational expression that we have, which is P of X over Q of X. Now, the fundamental theorem of algebra also lets us write it as the sum or difference of a bunch of smaller, proper, rational functions. In other words, we've broken it down into something simpler. This is getting back to what we started with at the very beginning of this section up here. In other words, the fundamental theorem of algebra lets us take this more complicated fraction on the right and break it down into the sum of these simpler fractions on the left. So the fundamental theorem of algebra guarantees that we can factor the denominator and that we can rewrite it as the sum or difference of simpler fractions. And that becomes one of the most important concepts that we're going to be covering, which is why it works. Now, what do we mean by proper rational functions? They're not just proper, they're of a particular form. Now, ax plus b is linear. Why? Because x is raised to the first power. So if this is linear, what degree is a by itself? Now, a represents a constant. All constants have degree 0. So the numerator is degree 0, denominator is degree 1. That makes this proper, right? Degree of the denominator is bigger than the degree of the numerator. It could be raised to a repeated power. In other words, it could be there more than one time. The other possibility from the fundamental theorem of algebra is that we have an irreducible quadratic factor, which you see here on the right side. So we have something like ax squared plus bx plus c, and it doesn't factor anymore, all right? So whatever it represents, it doesn't factor anymore, and it may be there more than one time. Now, the numerator could either be a by itself or ax plus b to make it proper. We normally go with 1 degree less, so we'll use ax plus b. That's degree 1, whereas the degree of the denominator is going to be degree 2, possibly raised to a power, which would change the degree a little, but I think you get at what I'm talking about. The degree of the factor is 2, so the degree of the numerator is 1 less. Now, this is guaranteed by the fundamental theorem of algebra, which is pretty sweet when you think about it. That guarantees that we can break apart rational expressions into simpler rational expressions, added and subtracted together. Now, what's the next thing we want to take a look at? One of the things that we want to consider when we're doing this, before I go on to types of rational function denominators, is that the denominator does need to be fully factored. We're going to have to factor q of x completely. We don't really want p of x factored. If it is, you probably have to undo it and multiply it back out again. We don't want to factor the numerator. We don't even focus on the numerator at all. We're focused on the denominator and using the fundamental theorem of algebra to decompose it. So let's now consider the 4 different types that we talked about a minute ago for the denominators. Remember, we could have just distinct linear factors, or we could have at least one linear factor that repeats, raised to a power bigger than 1, or we could have an irreducible quadratic factor, that's the 3rd, or we could have an irreducible quadratic factor raised to a power, that's the 4th. So we've got these 4 basic types, and we can have combinations of these as well. So again, what we're trying to do is break down these complicated rational expressions into something simpler, with the ultimate goal being to be able to integrate the simpler expression. So we want to take Q of X and we want to factor it into however many factors it goes. Now, this has K different factors right here. It'll be rare for us to have more than 3, at most like 4. I mean, 4 would be pretty overkill. So we're not going to have that many. But what we're getting at is this idea that whatever this complicated rational expression is, we can break it down into the sum and difference of these simpler ones right here. Now we're starting with case 1, which is that the quotient, the denominator, Q of X, in the bottom has distinct linear factors only, right? So only linear, x to the first, and all different. If that's the case, it can be written as the product of all those linear factors, and there must be a way to split up the more difficult, complicated rational expression we started with into the sum and difference of simpler rational expressions where the denominator of each one is one of those distinct different factors. Now we're going to go through some examples of what this looks like so that you can see it. So if you're like, I'm not quite following, just hang with me. It'll make more sense in a minute. Now, when the factor in the denominator is linear, the unknown that goes in the numerator above it will be a constant. Here they're called A1, A2, up to A sub k. We typically will call them A, B, C, D, E, F, G. It'd be shocking if you had to get to H and I, but I think I have seen a homework problem that gets out to I, but not anything really past that. All right. Note that each individual fraction is proper. The degree of the numerator is 0, degree of the denominator is 1. So each of these is a proper fraction. And instead of integrating this complicated thing on the left, we can split this into k different integrals and integrate each one on the right independently. And they'll all be u substitution 1 over u du, basically, by the time we're done, which is the natural log of the absolute value of u. So these are pretty straightforward. I mean, we just talked through how to integrate them. The problem is we have to figure out how to split them up, and we've got to be able to find these constants in the numerator. So this is going to be what we're looking at now. Now let's take a look at some examples of some polynomial expressions. I've got x squared minus 3x minus 10. Assume this is a denominator. It does factor x plus 2, x minus 5. They're different. That means distinct. And they don't repeat. And they're linear. Different, distinct, don't repeat, not raised to a power. And they're linear factors. X to the first plus 2, x to the first minus 5. So each of these only occurs once, and it's linear. This is case 1. Let's take a look at the next example down here, which is x to the third minus 5x. Now we've got a common factor of x, so we factor out the monomial x, and that leaves an irreducible quadratic x squared minus 5. This is not an example of non-repeated linear factors because x squared minus 5 is not linear. The degree of this factor, just the factor itself, is degree 2. Now, if you look at the x by itself, it is x to the first. We consider all monomial x expressions to be linear. So even if you had something like x to the 5th, I'm going to think of it as x plus 0 quantity to the 5th. So even if it's x to the 5th, I'm going to consider it to be a linear factor repeated 5 times, right? Does that make sense? Let me say it again. If I have x to the 5th, I'm going to think of it as x plus 0, quantity to the 5th, meaning it's a linear factor, x plus 0, repeated 5 times. So all monomial x factors are considered linear. So this one is not a linear expression. It's not case 1 because x squared minus 5 is not linear. Looking at x squared minus 4x plus 4, it factors as x minus 2 times itself, which is x minus 2 squared. Now the factor itself is linear, x minus 2, because it's x to the 1st minus 2, but it's repeated. It's there twice. So it's not a distinct non-repeated linear factor. This is going to be case 2, not case 1. Case 1, they're all different and they don't repeat. All right. So now we want to take a look at example 1. And in example 1, we want to break apart this rational expression that you see here into the sum or difference of proper rational functions with some unknown numerators. We won't know what they are yet. We haven't learned the method of partial fractions yet, using the fundamental theorem of algebra to break apart the denominator. So we just want to do one step at a time. So the first thing that we're going to do is we're going to take this expression, 2x squared minus 9x minus 9. We're going to ignore the numerator and we're going to focus on the denominator. We want to fully factor the denominator. So this is going to become, leaving the numerator alone, focusing on the denominator. First, we take out the common linear factor of x, and then we need to factor the quadratic factor x squared minus 9, which does factor further. So our completely factored denominator is x minus 3 times x plus 3. So that is our completely factored denominator. Now, what does the fundamental theorem of algebra guarantee? It guarantees that this expression that we started with, which is equivalent to these two, can be broken down into the sum or difference of simpler fractions where we have an unknown numerator over each distinct linear factor in the denominator. And this is what I mean by decomposing the original expression into the sum or difference of simpler expressions. And I keep saying or difference, but these are both plus. But I don't know what A, B, and C are yet. If B is negative, then you could think of it as subtraction. That's why I keep saying sum or difference. Until we know what A, B, and C are, we won't know whether these signs in between are positive or negative. So we don't know if it's really a sum or a difference. So this is the method of decomposing the original rational expression into the sum of simpler rational expressions where each distinct non-repeated linear factor shows up one time with an unknown numerator. This is guaranteed by the fundamental theorem of algebra. There have to be numerators such that when I get common denominators and combine these, I can get back to here. There has to be. That's the fundamental theorem of algebra. Let's now take a look at case 2. In case 2, we again have only linear factors, but we have a repeated linear factor. So let's say that we have this a1x plus b1 is repeated m times. In other words, it shows up that to the nth power in the factorization of q of x, where q of x is the denominator of the rational expression. So remember, our rational expression is really p of x over q of x. And when we factor q of x, we have this repeated linear factor in the denominator. Now, to decompose it, instead of just the single term of a over the linear factor, we're going to actually have one separate term for each successive power that shows up in the denominator, which sounds kind of crazy, but this is why it works when you think about having common denominators, what you're going to end up with then is a1x plus b1 to the first power, a1x plus b1 to the second power, a1x plus b1 to the third power, then to the fourth, to the fifth, to sixth, all the way out to the nth power. And each one of the numerators is some unknown value, some constant. Why constant? Because these are linear factors. The factor itself is degree 1, so the numerators have to be degree 0. Not the degree of the whole denominator, the degree of just the factor, right? Which is the a1x plus b1. So this sounds kind of crazy. So let's take a look at a couple different examples that I've got written out here. So let's take a look at these examples. So I have the expression 6x plus 5 divided by the quantity x minus 3 quantity squared. X minus 3 is the factor that repeats. It's there 2 times. It's linear because it's x to the first minus 3. So it's a linear factor. So when we decompose this more complicated one on the left, we'll have x minus 3 to the first power plus x minus 3 to the second power. We need 2 fractions because the linear factor was there 2 times. And the numerators are unknowns. They're a and b. The 3 methods we talked about earlier, Heaviside Method, choose wisely, and equating coefficients, will be used to find out what a and b are in order to make this a true statement. But right now, we're just trying to decompose. Let's look at this second example here, x squared minus 4x plus 2, all divided by the repeated linear factor x plus 4 to the third power. It's there 3 times. It is linear because it's x to the first plus 4, but it's there 3 times. So I need a denominator of x plus 4, a denominator of x plus 4 squared, and a denominator of x plus 4 cubed. And then the numerators are again unknown. We don't know what they are yet. The method of partial fractions will let us find those out. The last example that we have down here actually has 2 repeated linear factors. We have 5x plus 8 in the numerator, x minus 1 squared times x plus 3 quantity squared in the denominator. So I have 2 linear factors, x to the first minus 1, x to the first plus 3, and they each show up twice. So what do I need over here? Remember, when we're decomposing, each decomposed denominator consists of 1 factor or 1 factor raised to a power. So I could have x minus 1 or x minus 1 quantity squared or x plus 3 or x plus 3 quantity squared. And each of those has an unknown numerator. And there must be a way, and there must exist A, B, C, and D, such that when we get common denominators and combine this right side, we get the left side, guaranteed by the fundamental theorem of algebra. Let's take a look now at example 2 and practice decomposing this rational expression you see here into the sum of proper rational functions with unknown numerators, using the fundamental theorem of algebra to decompose the denominators. Now, the denominator that you see right here is this x plus 1 quantity to the third. So what are we going to have when we break this apart? So we have 2x squared plus 3x plus 3 divided by the denominator x plus 1, the linear factor, cubed. Now what are we going to do? What are we going to have after that? The next thing we need to do is we know we need to break down the denominator. It's a 1 factor, x plus 1, repeated 3 times, which means I could have a denominator of x plus 1 or a denominator of x plus 1 quantity squared or a denominator of x plus 1 quantity cubed. Those are the 3 possibilities for breaking that apart. And then the numerators are unknown. So I have A, B, and C in my numerators. Those are the unknowns. Now again, when we get to the method of partial fractions, We'll learn 3 techniques of finding A, B, and C, but right now we're just learning to decompose into these simpler fractions. Then we'll learn how to find A, B, C, and we'll put it all together and actually integrate some of these more complicated rational expressions. Let's look at case 3 now. What is case 3? Case 3 deals with a distinct, different, irreducible quadratic factor. So we have irreducible, meaning it doesn't factor, and it's quadratic. Remember, the fundamental theorem of algebra says that all polynomials are the product of linear factors and irreducible quadratics. So I don't care what the degree is, you have to be able to factor it somehow, some technique, into linears times quadratics that don't factor any further. You don't need any cubics or fourth degrees. Those factor more, right? So they have to be able to be broken down. So in order to do this, the numerator is going to be exactly 1 degree less than this irreducible quadratic, which means it will be linear or degree 1. So looking down here, we can see that the irreducible quadratic factor could be ax squared plus bx plus c. And to make the numerator precisely 1 degree less, we make it linear, capital AX plus capital B. Now the capital A and the lowercase a, they're not related. The capital B and the lowercase b, they're not related, right? They are not related. They are all constants, but they are not related. They're all real numbers, but they're not related. Let's take a look at some examples of how to decompose with irreducible quadratic factors that are different. So here's the first one we want to take a look at. We have 4x plus 5 in the numerator divided by the linear factor x minus 1 and the irreducible non-factorable quadratic factor x squared plus 3. So we can split this apart. We need one term with the linear factor x minus 1 because it only shows up one time. And we need one term with the irreducible quadratic factor x squared plus 3. Now what needs to be in the numerator? X minus 1 is linear, so the numerator has to be a constant, degree 0, so it's going to be a. X squared plus 3 is quadratic, so the numerator has to be linear, 1 degree less, uppercase bx plus uppercase c, right? Now let's look at this next example that we have here. We have x squared plus 4, irreducible quadratic here, and we have x squared minus x plus 3, which is also an irreducible quadratic factor. Neither one of these factors any further, which means when I break it apart, they only show up once, so I need one for each of them, one term for each of those distinct factors, and the numerators have to be linear in order to be precisely 1 degree less than the factor in the denominator. They're always either going to be constant or linear because that's what we have. All right, let's practice this on example 3. On example 3, we have x cubed plus 3x squared plus x plus 9 divided by the irreducible quadratic x squared plus 1 and the irreducible quadratic x squared plus 3. We have x squared plus 1 showing up one time in the original denominator, so it needs to be there one time. It is quadratic, so its numerator must be linear, ax plus b. Then we need one term for the other factor in the original numerator, x squared plus 3. It's quadratic, so its numerator also must be linear, cx plus d. And we tend to go alphabetical. Like I said, we're not going to have that many factors in our denominators because it gets crazy, right? Trying to solve that. We'll probably on average have 2 to 4, and that's about par for the course. On a rare occasion, you might have 5 or one of them is a repeated factor, or 2 of them are repeated factors. So this is what we're going to have as our result when we decompose this complicated rational expression. There have to exist uppercase A, B, C, and D that would make this true. And then instead of having to integrate this one on the left, I could split the integral into the two simpler fractions on the right, and I could integrate these using simpler techniques that we have already learned. Okay? Let's now take a look at case 4. Case 4, as you might expect, has an irreducible quadratic factor, but it repeats. So we've had linears that don't repeat, linears that do repeat. Irreducible quadratics that don't repeat. Now we have irreducible quadratics that do repeat. So how do we deal with that? Well, what do you think we're going to do? We're going to do what we did with the repeating linear factors, which means it has to show up that many times, one for each possible power of the irreducible quadratic factor. So we're going to have one successive or one term for each successive power. So when we're looking at it, if our irreducible quadratic is this a sub 1 x squared plus b1x plus c1, then I need that to the first, that to the second, that to the third, that to the fourth, that to the fifth, out however many times it repeats in the original rational expression denominator. And each numerator has to be degree 1. They all have to be degree 1 because the factor, not the denominator, but the factor itself is quadratic, which is degree 2. So the numerators are all degree 1, which are basically linear. For us, again, most of the time we have so few that we can, instead of using subscripts, we can just use the letters of the alphabet in the uppercase format for our numerators, and this will let us find it. So to repeat, our unknown numerators are always either going to be constants, A, B, C, D, when our denominators are linear factors, or they're going to be linear expressions, ax plus b, when the denominators are irreducible quadratic factors. Let's practice this on a couple of examples. When we're looking at this expression that we see here, we have a denominator of x squared plus 1 raised to the second power. So it repeats twice, it's there 2 times, and x squared plus 1 does not factor, so it is an irreducible quadratic. That means that we need it to be to the first power in one denominator and to the second power in the next denominator. Both of these are based on a quadratic factor, so both numerators must be linear, ax plus b in the first and cx plus d in the second. We tend to go in alphabetical order. What about this one right here? We have the irreducible quadratic factor x squared minus 5 present 3 times in the denominator. So we need a denominator of x squared minus 5 to the first power, x squared minus 5 to the second, and x squared minus 5, ooh, I have a typo, or it's just missing, to the third. Make sure that that shows up right there, right? Looks like it, the columns are sort of cutting it off, but it should be to the third, right? Now, notice that all 3 of the numerators have to be linear because the factor on which they're based is quadratic. Now let's practice doing this on example number 4, where we have the quantity x plus 3 divided by the product of x minus 1 and x squared plus 1 squared. We have one linear factor of x minus 1, which shows up 1 time. So the numerator, because the factor is linear, the numerator has to be a constant. We'll call it a. The next factor that we have is x squared plus 1, which is an irreducible quadratic. It doesn't factor, and it shows up twice. So we're going to need x squared plus 1 to the first, and we're going to need x squared plus 1 quantity squared. Now, these are both based on the factor x squared plus 1, which is quadratic, so their numerators have to both be linear. So keeping in the alphabetical order, I'll have bx plus c over the first plus dx plus e over the third, or the second one for that repeated quadratic factor. Okay, so hopefully this is making sense to you of what we're doing right now and how we're splitting these apart and how we're decomposing them. Now, I want you to keep in mind that powers of x are always considered to be linear. They're never considered to be quadratic or anything else. They're always linear. So if you have something like x to the fifth, we're going to think of this as x plus 0 to the fifth. So it's always linear, which means that you would need to break it apart, and you would need to have an a over x plus a b over x squared plus a c over x cubed plus a d over x to the fourth plus an e over x to the fifth, if that was in your original denominator. That's how you would decompose it. And you can tell that it doesn't take much to really expand those right-hand sides. But again, it's much simpler to integrate something like this than it would be to try to integrate what's on the left, if it's even possible. We have now finished talking about the types of denominators that we're going to be decomposing. So we're ready to talk about the methods of breaking down these rational expressions. So again, there are three basic methods. And when we talk about methods, what we're talking about is, how do I find those A's, B's, C's, D's, E's, etc., that are showing up in the numerator? How do I pinpoint what those constants are? And they are constants. They're linear constants, or real constants, and they're attached to the linear expressions or just the constant itself. So these three methods are the Heaviside method, choose wisely, and equating coefficients. Equating coefficients always works. Choose wisely always works. Heaviside does not always work. However, Heaviside is probably the fastest and easiest, and it does work on linear factors. So we're going to start with the Heaviside method. This is not going to work for quadratic factors, and it only works on repeated linear factors for the highest one, not for the lower powers of the repeated ones. So we're going to start with all distinct linear factors and talk about how that works. Now, I will tell you that the Heaviside method is not my favorite method because it's very procedural. It's not based on mathematically precise techniques, and so it's not my favorite because if you remember how to do it, then you can do it, and if you don't remember how to do it, you can't derive it. So it's not my favorite method. My favorite is what we call choose wisely, or equating coefficients. But let's go ahead and demonstrate it, because a lot of students find that the Heaviside method is fast and easy, and they do like it. So again, you're welcome to use it if it makes sense to you. We're going to start with the rational expression 7x minus 4 divided by the quantity x squared minus 2x minus 8. It is a proper fraction. Degree of the numerator is 1. Degree of the denominator is 2. What are the steps of the Heaviside method? Here they are. Factor the denominator completely. Do not factor the numerator. If it's factored, just leave it or multiply it out, but probably you're going to need it multiplied out at some point, but leave it. So we factor it completely into x minus 4 times x plus 2. Then we're going to decompose that using the method that we just talked about with the 4 cases 1 through 4 up above. So now we decompose this. We have 2 linear factors that are distinct, different, and don't repeat. So we have the first linear factor, x minus 4, in the denominator of one fraction, and the second distinct linear factor, x plus 2, in the denominator of the other one. Now the numerators of those fractions is unknown. Those are a and b. That's what we're looking for now. We're on to methods of partial fraction decomposition. So we've learned how to decompose, but now we've got to find the A's, B's, and C's. So now what do we want to do? Well, we're going to take the original factored fraction and set it equal to the broken down term. So we're just back to starting with this. So this is our original. We've decomposed it into the sum of the two fractions on the right. Now here's the part I don't like. What you're going to do is you're going to take your hand or your finger and you're going to cover up one of the distinct linear factors in the denominator on the left, so where it was completely factored. In this case, you'll see that x minus 4, that factor, has a translucent blue box on it, which represents covering it up. So what we would have left on the left would be the 7x minus 4 in the numerator and the x plus 2 in the denominator. Now, we didn't cover up anything on the right side, so we still have the right side the same. To find a, which is the numerator of the factor we covered up, right? So x minus 4 is what we covered up, and its numerator is a. To find a, we're going to take the solution associated with that factor. If the factor is x minus 4, setting it equal to 0 and solving gives us x equal 4. We're going to take that 4 and we're going to plug it in to the expression that's on the left side, except for the part we covered up. And you can see why I don't particularly care for this method. This is not mathematical at all. Why do we do it? Because it works, all right? So there are some complicated mathematical reasons why it's correct, but again, it only works in certain cases. It's not my fave. Okay, so we take this right here, and we're going to cover it up. All right, and then we're going to take the solution 4 to the factor x minus 4, and we're going to substitute it into what's left, the 7x minus 4 over the x plus 2. We represent this with the long vertical bar on the right with x equal 4 on the bottom. When we substitute it in, we get 7 times 4 minus 4 in the numerator over 4 plus 2 in the denominator, which when reduce it, we get 4. Now, the fact that it's another 4 is just accidental, all right? Totally not important at all, all right? Just a fluke that we got the same number. In other words, a is 4, all right? You may say, what? That's crazy. Yeah, it's a little crazy. But that's how you find A. A is 4. Now, how do you find B? Well, you want to cover up the factor x plus 2. And if you're covering up the factor x plus 2, the solution to x plus 2 equals 0 is x equal negative 2. So now we're going to take into what's left on the left side after we cover up the factor x plus 2. And we're going to substitute in the value x equal negative 2, which is the solution to that missing factor. Now, why wouldn't we substitute it into the missing factor? Because it would give you 0 in the denominator, obviously, and 0 in the denominator is bad, bad, bad. So we don't do that. When we substitute it in, we end up with 3 for the value of b. So this is the Heaviside method in a nutshell. You're covering up one factor at a time, substituting the solution of that factor into the parts on the left that are not covered up, and that gives you the value of the numerator over that covered up factor on the right. So the decomposed fraction of 7x minus 4 over 2x squared minus 2x minus 8 becomes 4 over x minus 4 plus 3 over x plus 2. Now, the whole point to doing this is integration. That's what we're learning in this particular chapter, which is techniques of integration. So if we had an integral on the left, we could instead integrate the two integrals on the right. Now, the one on the left, I wouldn't know how to do this really without the method of partial fractions. It's not use substitution. There's not an easy way to go about this. Yeah, I can maybe try splitting it into 2, maybe do some kind of weird manipulation to try to get it to be use substitution and trig substitution, but it would be awful, right? Really nasty. The ones on the right, though, are quite simply use substitution, where u becomes the denominator, either x minus 4 or x plus 2, 1 over u du, natural log of the absolute value of u. And it would be simple to go ahead and integrate those. Let's take a look now at example 5, which is basically example 1 again. So I've gone ahead and I've recopied the work that we did in example 1 to decompose this right here. And what we want to do this time is we want to find A, B, and C using the Heaviside method. Okay, so when we're looking at these, what I want to do is I'm going to start with the left-hand side, 2x squared minus 9x minus 9 over the factored denominator x plus 3, x minus 3. So I'm going to do this in some different colors. So I have 2x squared minus 9x minus 9 over x plus 3, x minus 3 equal a over x plus b over x plus 3 plus c over x minus 3. Okay, so this is what we have each time. Now, what I want to do here, I'm going to copy this off so that I can paste it down below in just a moment. What I want to do each time is I want to go through and I want to cover up one of the linear factors. They're all different. X by itself is a linear factor. X plus 3 is a linear factor, and x minus 3 is a linear factor, and they don't repeat, right? They each show up one time. So the next thing we want to do is we want to cover one of them up and substitute the solution to that one into what's left on the left. So what I'm going to do now is I'm going to cover up one of the factors, which in this case is the factor x. So what am I looking to find? I'm looking to find a. I'm looking to find a because a is the one over the x. And what am I going to substitute into this? Well, the solution for the factor x is 0. X equals 0 is x equals 0. So I'm going to substitute 0 into what's left on the left-hand side. So this is going to basically give me 2 times 0 squared minus 9 times 0 minus 9 over, remember what's left, 0 plus 3, 0 minus 3. And this is supposed to give me the value of a. All right, so I'm covering up what's left on the left side. This is going to give me negative 9 in the numerator and 3 times negative 3 or negative 9 in the denominator, which gives me 1. So a is equal to 1. So now I know that this particular fraction becomes 1 over x. Now I want to repeat the process and I want to find b, and then I'll repeat the process to find c. So I'm going to paste back in what I had originally. And now I want to cover up a different linear factor. So in this case, I'm going to cover up the x plus 3. What am I going to be looking for? Because I covered up x plus 3, I'm looking for the numerator of that decomposed factor, and that's going to be b. So I know that b has to be equal to this particular one with the solution to that factor. And the solution to x plus 3 equals 0 is x equals negative 3. So this is going to give me 2 times negative 3 squared minus 9 times negative 3 minus 9 in the numerator over what's left in the denominator is negative 3. Omit the factor you covered up, negative 3 minus 3, which is going to give me, well, this is going to take me a little more work. 9 times 2 is 18 plus 27 minus 9 is, I'm getting 36 in the numerator. Is that what you're getting? I hope so. And then in the denominator, I have negative 3 times negative 6, which is 18, I believe. And 36 divided by 18 is 2. So B is 2. And now let's take a look at doing it the third time to find C. So we want to do it one more time in order to find C. This is using the Heaviside method. So the one we haven't found yet is the one that is over the linear factor x minus 3. So we're looking for C now. And what we want to plug in is the solution that goes with that factor of x minus 3. And the solution that goes with that would be x equal 3. So this is going to give us the value of C, which is going to be 2 times 3 squared minus 9 times 3 minus 9 divided by 3 times 3 plus 3. So in the numerator, that gives me 9 times 2 is 18 minus 27 minus 9 over 3 times 6, which is 18 again. That's 36. I'm getting negative 18 over 18. Is that what you guys are getting? Let me check my work and make sure that I haven't made a mistake. And that's what I have. And now we're ready to go ahead and decompose this into what we originally had. So this expression that we see right here is going to get decomposed into 1 over x. I can't remember what b was. 2 plus 2 over x plus 3 minus 1 over x minus 3. Let's write that down at the bottom here. So our expression, 2x squared minus 9x minus 9 divided by x cubed minus 9x can be rewritten into the sum and difference of simpler rational functions 1 over x plus 2 over x plus 3 minus 1 over x minus 3. And this is what we would call a partial fraction decomposition, with the goal being to integrate the expression on the left by instead integrating the expressions on the right. Now let's look at the last case where the Heaviside method does work a little bit. The Heaviside method is really best for linear factors that don't repeat. Now, you can use it on repeated linear factors only for the highest power of that repeated factor. So it only gives the highest power of the repeated factor. It won't work for the lower powers of the repeated factor. And it also requires that you have at least one non-repeated linear factor or a quadratic factor. In other words, you got to have something else in the denominator. It can't just be a repeated linear factor. So it won't work on example 2, which only had one repeated linear factor in the denominator. You've got to have more than just the one factor present. You've got to have multiples. So let's take a look at that. Looking at this one right here, we have 2 linear factors, x minus 1, which is repeated twice, and x plus 2, which is not repeated. So again, I've got a repeated factor, but I have another factor as well in the denominator. So I should be able to use the Heaviside method in order to be able to find the numerator over the x minus 1 to the second power. I won't be able to find the one of x minus 1 to the first power. All right, so let's go through the method. We start the same way we did before. We factor the denominator completely. Don't factor the numerator. It's just wasted effort. We're not going to want it factored anyway. Then we break down the fraction using cases 1 through 4. So we have a repeated linear factor. So we have it there to the first power, and we have it there to the second. And then we have the non-repeated linear factor present one time. Set the original factored fraction equal to the broken down terms. So this is my original fraction equal to the broken down terms. And cover up the repeated linear factor on the left side with your finger. So in this particular case, we want to cover up the x minus 1 quantity squared. Now, we're only going to be able to find the numerator over the highest power of that repeated factor. We're not going to be able to find this lower one with a in the numerator. We're only going to be able to find the b one, right? So what do? We cover this up, and then we repeat the process that we did before. We're going to substitute the solution to that factor of x minus 1, which setting equal to 0 would give us a solution of 1. We're going to plug that into what's left, and that will give us the value of b. So when we do this process, after covering up the x minus 1 quantity squared, we're left with 1 over x plus 2. We substitute the solution to the missing factor, 1, and that gives us that b is 1/3. Then we'll repeat the steps for any other distinct linear factors. Now, the a over x minus 1, that's not, I mean, it repeats, right? So we're looking for a different linear factor, which would be the x plus 2. So we're going to cover that one up. We should be able to find that one using the Heaviside method because, again, it's distinct. It's different from the others. So we cover up the x plus 2. The factor is x plus 2. The solution is x equal -2. And we substitute that into what's left after we cover up that factor. And we get that c is 1/9. Now let's replace what we found so far. What we found so far is the value of b is 1/3 and the value of c is 1/9, which you can write it in the numerator. You could move it out front to make it a little bit easier. But we were not able to find the lower power of the repeated factor x minus 1. So we weren't able to find a. Okay, so since this has to be true, though, for all values of x, since I'm only looking for one value, I found everything else. I found b and I found c. I only have one missing value. I should be able to substitute in any value that doesn't make a denominator 0 and get the value of a. So I look for an easy value to plug in. Now, the easiest value is 0. The next easiest is 1 and -1, and then 2 and -2. I wouldn't want to plug in a 1 or a -2. That would cause the denominator to be 0. But I could plug in 0. So if I plug in 0 on both sides of this equation, then I should be able to figure out what a is. And that's exactly what we do. So we plug it into both sides of the equation, and we do some algebra, okay, quite a lot of algebra. And we end up with this expression over here, which when we finally reduce it tells us that a is a -1/9. And then we can rewrite the decomposed rational expression in this way right here. So this last part, step 8 and 9, or step 8 really, is actually the choose wisely method. So we're just choosing a wise value to plug into the thing and so that we can find the missing value. So it's really choose wisely, right? So this is the method that is the Heaviside method. And again, I most recommend using it to find the numerators of the distinct linear factors or the highest repeated linear factor. That's the only time we can really use it. It's not my favorite method. I've said that before. If you like it, you're welcome to use it. But my favorite method is what I call choose wisely. So let's focus on choose wisely now. Choose wisely is a method that will always work. It does sometimes actually devolve into equating coefficients, which is actually method 3. So we saw that Heaviside actually kind of veers into choose wisely, and choose wisely will veer into equating coefficients. So on rare occasions. So what is this? How do we do this one? This one works by deliberately choosing values that would give you 0 in the denominator. And now that sounds crazy. Why would we do that? Well, we're trying to get certain factors to disappear out of the expression. So I'm going to go back through example 1 again, which is also example 5, same thing. So we're going back through this same problem, but now we're going to do the method of choose wisely. So when we're looking at this, we're going to factor the denominator completely. Don't factor the numerator, it's wasted effort. So you get this expression right here. Then we're going to decompose the denominator into the sum of simpler fractions with the linear factors in each denominator And if there's repeated ones, they are each power of the repetition is there as well. All right. If there are quadratic factors, we'll have quadratic factors as well with linear numerators. So we're going to break it down. So far, it's the same as Heaviside. Set it equal to the original rational expression with the factor denominator. Same method as Heaviside. The next step is where they veer widely and go in different directions. This is mathematically correct, and it's not something that you have to, some weird technique, cover this up, plug this in. You don't have to do that. This makes sense. Get rid of the fractions by multiplying both sides by the common denominator, which is the fully factored denominator on the left. So we're going to multiply each term, all three, by the fully factored denominator on the left. Now, by doing this, of course, we're assuming that x is not 0, x is not 3, and x is not negative 3, because if it was, we'd have 0 in the original denominator, which is a no-no. So this is to get rid of the fractions. And when we're done, we have the numerator from the left, and then we have the numerators from the right multiplied by the factors they did not have in the denominator. Now we're going to choose wisely. So basically, we multiply by the LCD to get rid of the fractions, and then we deliberately choose those values that would have given us 0 in the original denominator. In other words, we choose x to be 0, we'll choose x to be 3, and we'll choose x to be negative 3. In doing that, whichever term has that factor in it will drop out, and it will allow us to write equations in terms of what's left. So let's go through and see what we do. We're going to start with the factor of x from the original denominator. We're going to substitute x equals 0 into the left side and x equals 0 into each of the terms on the right side. So on the left side, any term with x in it drops out, and I just get negative 9. On the right, any term that has the monomial x drops out, because that's 0 and that's 0. So it doesn't matter what the other parts are. 0 times anything is 0. So the second two drop out. And we're left with a times 0 minus 3 times 0 plus 3, or 9a. Right? Negative 9a. So we end up with negative 9 equals negative 9a, and we get a equal 1. Right? I know, it's beautiful, isn't it? This is my favorite. Okay. Now let's repeat step 5 for the other two distinct factors. We have the factor x minus 3. So its solution is 3. So we're going to go back to the original after we eliminated the denominators, and we're going to substitute 3. So back to the original again. Now we're going to substitute 3. It's a little more work because we have to replace the x's with 3's. But any factor on the right that has x minus 3 is going to drop out, because 3 minus 3 is 0. 0 times anything is 0. So the first one drops out and the last one drops out, and we just get the middle one, b times 3 plus 3, which gives us 18b. And then when we work this out, we get b equals negative 1. And then we can repeat the last one, which is the factor x plus 3, which has solution x minus 3. Anything that has the factor x plus 3 is going to disappear and drop out because it'll be 0. And then we'll be left with just this factor term on the right. And we get that c is equal to 2. And then we can write our decomposed expression like this. This is my preferred method of doing it. Now, occasionally, we will need to actually just pick another value because we'll still have some unknown left. And so we'll have to pick another value. This happens sometimes when we have quadratic terms, right? Let's talk about equating coefficients. This is the third method, and actually the one from which the other two originally came. So it is the one that works in all cases, no exceptions, but it can be a lot of work, right? So it is the one that produces the most stuff, but again, it never fails as long as you're careful, all right? This is the oldest method. So here's the idea behind equating coefficients. We're going to start with example 7, which is actually example 2 again. And we're going to go back and we're going to look at the decomposition of it. So we're looking at this one right here, and we're going to factor the denominator completely, which it's already factored completely. It's x plus 1 quantity to the third. So it is factored as much as it will go, all right? Then we're going to break down the fraction on the left by decomposing it. So it's a repeated linear factor. The linear factor is x plus 1. So we get a over x plus 1 plus b over x plus 1 quantity squared plus c over x plus 1 quantity cubed. Remember, when the linear factor shows up multiple times, you need one denominator for each power, right? But the factor itself is linear, so all numerators are constants. Okay, so far it's exactly the same as the first two methods. Step 3, set it equal to the original, same as the first two methods. Step 4, basically the same as choosing wisely. Multiply every term on both sides of the equation by the lowest common denominator. This cancels the like fractions or like factors. So this gets rid of the fractions. This is the same as choose wisely. So we end up with this expression right here, this equation, without fractions in it because we multiplied both sides by the lowest common denominator. Now, the next thing that we're going to do is we're going to solve this by basically multiplying everything out. That's why I said you have to be careful. There's just lots of multiplication involved. So count the number of unknowns that you have. You have A, B, and C, which means you'll need at least 3 equations to solve this. It's going to form a system of equations. And for every unknown, you have to have at least one unique equation. So we need at least 3. We could have 4 or 5, but that would be overkill. We have to have at least 3. If we only have 2, we can't solve it. Next thing we want to do is fully multiply out both sides of the equation. So by that, I mean square the x plus 1 and multiply what's left by a, and distribute the b over the x plus 1. So you'll see that I did that in this step right here. The next thing we want to do is gather the like terms. So everything that has an x squared on it gets written together with the x squared factored out. There was only one. And then everything that has an x in it gets written together with the x factored out. We had a 2ax and a plus bx. So we get a 2a plus b quantity times x. Everything else becomes part of the constant, the coefficient at the end. Now we call this equating coefficients. For this equation to be true, the coefficient of x squared on the left has to equal the coefficient of x squared on the right, which means that a has to be 2. That's one equation. The coefficient of x on the left, which is 3, has to be equal to the coefficient of x on the right, which is 2a plus b. That's a second equation. Our third equation is that the constant on the left, which is 3, has to be equal to everything else, the constant on the right, which is a plus b plus c. This gives us 3 equations and 3 unknowns. All right? Here are our 3 equations. A equal 2, 3 equal 2a plus b, and 3 equal a plus b plus c. Then we're going to substitute for any known value. So if a is 2, I can substitute it in the second equation. And that gives me 3 equal 4 plus b, so b is -1. So now I know a and b. I can substitute those in the third equation, and I can get that c is equal to 2, right? So this is called the method of equating coefficients. However, it can involve a lot of detailed multiplying out of polynomial expressions, we have to be careful not to mess up any signs, right? No signs and no constant coefficients, or the whole method just devolves into super, super nasty fractions, all right? And then, of course, you go ahead and rewrite the expression in its decomposed form. Now let's take a look at what we've done so far. We want to look at example 8 again, which is examples 1, 5, and 6. We've done this one multiple times. At this point, we've looked at it several times, but now we actually want to integrate it, right? So we've done this one multiple times. So what we want to do is we want to go ahead and break this one down. We have broken it down before. We've gone through this one multiple times. And what we have found is that this becomes, of course, 2x squared minus 9x minus 9 over factored x plus 3, x minus 3 dx. And when we decomposed it, we got 1 over x plus 2 over x minus 3, or x plus 3 rather, minus 1 over x minus 3. Right? This is what we got when we decomposed it using the method of partial fractions. So whether you did Heaviside, choose wisely, or equating coefficients, you got the numerator values. Now, because these are sums and differences, we can split the integral across the 3. And so the integral of that complicated rational expression on the left becomes the integral of 1 over x dx plus 2 times the integral of 1 over x plus 3 dx minus the integral of 1 over x minus 3 dx. Right? Hopefully I said that right. Okay, which is what we have here. Now what do? Well, I know what this one is. It's just the natural log of the absolute value of x, right? That one's done. And of course it has a constant. What about the second two? Well, they're u substitution, but I can let u be x plus 3 and du is dx. So it's really 1 over u du again. So this becomes 2 times the natural log of x plus 3. And the last one becomes minus 1, the natural log of quantity x minus 3 in absolute values plus constant. And we're done. That's it. So the actual integration on this one is quite simple. It's just 1 over u du. The method of decomposing it to get it into a form where we can integrate, that took a little work, right? We had to do the method of partial fraction decomposition or rationalizing functions. Let's take a look now at another example. We want to take a look at example 9, which is examples 2 and 7 again. So we decomposed it and we got these expressions right here, right? So these were our decomposed expressions that we came up with. And what would we do in these particular cases? How would we integrate these particular problems? Well, we're going to break it apart into the sum and difference of these different integrals. So this becomes 2 times the integral of 1 over x plus 1 dx minus 1 times the integral of 1 over x plus 1 quantity squared dx plus 2 times the integral of 1 over x plus 1 quantity cubed dx, right? So we've split it now into 3 simpler integrals of fractions. Now the first one is again going to be 1 over u du, where u is x plus 1. So looking at this particular one, I have u equals x plus 1, and my du is dx, so I get 1 over u du. So this is going to become 2 the natural log of the absolute value of x plus 1 plus the constant of integration. Well, what about this guy? Well, Actually, this is even easier. It's just use substitution. I could rethink of this particular one instead as negative the integral of x plus 2 to the negative 2 dx. I could let u be x plus 2 and du would be dx. So this becomes u to the negative 2 du. Well, what's the integral of u to the negative 2 du? U to the negative 1 divided by negative 1. And so when I work that one out, I get minus x plus 1. How'd I get a 2 in here? That should be a 1. I think I was looking at my square. Okay, so I have x plus 1 to the negative 1, and then divided by negative 1, which is basically going to give me a plus 1 over x plus 1. So I have 2 natural log absolute value of x plus 1 plus 1 over x plus 1. And I can do the same thing for this third one over here. I can think of this as 2 times the integral of x plus 1 to the negative 3 dx. I can let u be x plus 1 again. Du would be dx. And this would become u to the negative 3 du, which would give me then plus 2 u to the negative 2 divided by negative 2. And then I've got my constant, all right? So my 2 divided by negative 2 would give me as minus 1. And I could write this as 1 over x plus 1 quantity squared plus c, right? So again, it's not that the integration itself is terribly difficult. The difficult part is decomposing it and getting it to a simpler sum and difference of simpler rational expressions that can be integrated more easily. Let's take a look at one that's maybe not quite as easy to do, where the integration is more difficult. So this would be example number 10. And again, we broke this one down into these two that we had right here. And let's take a look at see how we can equate coefficients. Now this one we haven't worked all the way out, so we're going to have to work this one out using the method of either equating coefficients, choose wisely, but we can't use Heaviside. Why can't we use Heaviside? Well, these are irreducible quadratic factors. So we could either do choose wisely, which is not a good choice here. Really the best is equating coefficients. So when we look at this one, what we want to do is we want to start by decomposing the rational expression in the integrand. So I'm going to take this and I'm going to multiply each side by the lowest common denominator, which is x squared plus 1, x squared plus 3, times x squared plus 1, x squared plus 3, times x squared plus 1, x plus 3, squared plus 3 rather, right? Now that cancels this denominator and that denominator, and that would leave me with x cubed plus 3x squared plus x plus 9 on the left equal the x squared plus 1 would cancel here, and that would leave me with ax plus b times the irreducible factor x squared plus 3 plus cx plus d times the irreducible factor x squared plus 1, since the irreducible factor x squared plus 3 would cancel, right? Now what I have is I've gotten rid of the fraction, right? So to equate coefficients, I'm going to go ahead and multiply everything out. Now, why wouldn't I use choose wisely? Well, because there is no value that's going to make this 0 and drop out. So choose wisely isn't a good option here. Heaviside's not a good option. I'm stuck with method 3, which is equating coefficients. So to multiply out the right-hand side, we're going to have to be a little bit careful here when we multiply it out. But basically, we end up with ax cubed plus bx squared plus 3ax plus 3b. Now that's from the first one, right? So I distributed the ax plus b over x squared and then ax plus b over 3. And now I want to repeat the process on this second term over here. But I'm going to line them up underneath like term under like term. So cx times x squared is cx cubed. So I'm going to put that under the other x cubed term. So I have a cx cubed. And then I have d times x squared. This needs to look more like a b. And this becomes dx squared. And then I have plus cx plus d. Right? So I can add these together now. What I have on the left is still x cubed plus 3x squared plus x plus 9. Combining my like terms, I have a plus c times x cubed plus b plus d times x squared plus 3a plus c times x plus 3b, oops, my b's are not going too well today, 3b plus d. And this last one, of course, represents the constant, right? Now we equate coefficients. So now that I have written them in the same format as what's on the left, I can equate the coefficients. The coefficient of x cubed on the left is 1, and the coefficient on the right is a plus c. So this gives me 1 equals a plus c. That's one equation. I have 4 unknowns, a, b, c, and d. So I need 4 equations. The coefficient of x squared on the left is 3, and the coefficient on the right is b plus d. So I have 3 equals b plus d. And then I have the coefficient of x on the left is 1, and on the right is 3a plus c. And then I have, making sure that I have all of this written down. The last one I have is the constant on the left is 9, and everything else on the right represents the constant. So I have 9 equals 3b plus d. Now this gives us a system of 4 equations with 4 unknowns, so we should be able to solve. The first thing I would do would probably be to take equations 1 and 3 or 2 and 4 and solve for A and C or for B and D. So go ahead and pause the video, work that out, then turn the video back on and compare your answers to mine. Okay, let's see what you came up with. So I took equations 1 and 3. I solved equation 1 for A, and I substituted it into equation 3. That let me get that C was 1, so A is 0. I did a similar thing for equations 2 and 4. I took equation 2 to solve for B. I substituted that into equation 4. That allowed me to find that D was 0, so B is 3. Now I want to go back to the original equation, and I want to rewrite what the expression is again. So it looks like I'm going to need some more space here. So let me add in a little bit more space, and then we'll start working out the rest of it. So now what we have is the original expression on the left, which was decomposed into these 2 simpler rational expressions with irreducible quadratic denominators. And then we found the values of A, B, C, and D so that our new reduced rational expressions become 3 over x squared plus 1 and 1x over x squared plus 3. And now we need to integrate those. So I'm not going to go through all of the details. I will write it down, and then I'll go through and show it slowly so that you can pause the video to see it. But basically, the one on the left has to be solved using the method of trig substitution. The one on the right can be solved directly using U substitution. So pause the video here, Work out the solutions, then turn the video back on and compare your answer to mine. Okay, so like I said, the first one becomes trig substitution. It's reminiscent of tangent squared of theta plus 1 because of the plus. You make your substitution equation here, rebuild the original denominator, reducing it into a single term in terms of theta instead of x, then find something to replace the differential dx with something in terms of d theta, and then substitute that into the integration. When you substitute it into the integration, you end up with secant squared theta d theta over secant squared theta, which just becomes d theta, which becomes 3 theta. Then using your substitution definition again up here, you know that theta must be the arctangent of x. What about the other one that we needed to do? Well, that's just basic u substitution. Looking at this, u is the denominator, find du, solve for it, 1 over u du, 1/2 the natural log of x squared plus 3, and then we have our constant of integration. So this completes the integration of that original rather complicated rational expression done using the method of decomposition with partial fractions. We have one more example that we want to take a look at now, which is going to be example 11. And it is rather more difficult. I'm not going to go through all of the details. I'm not even going to write it out for you, but I will tell you what the answer is. And we will go through the process of trying to find the decomposed expression so you know what it is you need to integrate. And I'll give you some guidelines on how you would do the integration as well. So this is the one that we're starting with right here, the integral of x plus 3 over the quantity x minus 1 times the quantity x squared plus 1 quantity squared. So we have a distinct linear factor, not repeated, and we have an irreducible quadratic factor, which is repeated twice. So when we decomposed it, we had x minus 1 once, x squared plus 1 to the first, and then x squared plus 1 to the second. Notice that the numerators of these become 1 degree less than the factor on which it's based in the denominator. Now what we want to do is we want to go ahead and we want to find the different values that we have here. We could use Heaviside on the x minus 1. We can also use choose wisely. We can also use equating coefficients. So whichever way you want to do it, let's decompose this and find the values of A, B, C, D, and E. So I'm going to let you pause the video here, work out what A, B, C, D, and E are going to be, turn the video back on, and we'll compare our answers. I'm sure it's quite some time later if you've been working through this, but let me show you an overview of what I did. I chose to do the method of equating coefficients with a little bit of choose wisely involved. So what I did was I multiplied both sides of the equation by the lowest common denominator to get rid of the fraction. And that gave me that expression that you see here in the middle. So let me highlight that for you right there. So that's what I ended up with when I got rid of all of the denominators by multiplying through by the lowest common denominator. Then I did choose wisely, where I let x equal 1 because I knew that would make this factor, this term here and this term drop out because the factor x minus 1 was present. And if x is 1, x minus 1 is 0. So doing that allowed me to figure out right away that A was 1. So I go ahead and I replace the A with 1. Now this gives me a new expression. And what I'm going to do now is I'm going to use the method of equating coefficients. So in order to equate coefficients, as awful as it is, you're going to have to multiply all of this out, which is enormously long, takes a lot of work, but let me show you how I organize my information. I create one row for each multiplication term that I have. So each one, so I had x squared plus 1 quantity squared. And then of course I knew that A was 1, so I could omit the A. That gives me x to the 4th plus 2x squared plus 1, which is way spread out because I'm leaving room for the terms in between. Now, the next one I had to do was I had to multiply x minus 1 times x squared plus 1. And then I had to distribute the bx plus c across it. So I did that in 2 lines. So first I multiplied it out and I distributed the bx across, which gave me this row here. And then I distributed the c across, which gave me this row here. Finally, then I multiplied dx by x minus 1, and that gave me this second to the last row. And then I multiplied e by x minus 1, and that gave me this row here. And then what I was able to do was I was able to gather together all of my common like terms. All my x to the 4ths here, x cubes here, x squareds here, x's here, and everything that wasn't one of those became a part of the constant. And then I equated my coefficients. So when I equated my coefficients on the left side, I didn't have an x to the 4th. So that's a 0 x to the 4th, which has to be 1 plus b times x to the 4th. So that gave me an equation over here that 0 is equal to b plus 1, which basically means that b is negative 1. So now I know a and I know b. And then I had the third one, which was the x cubes. I didn't have an x cubed on the left. So the left is 0 x cubed, which has to be equal to c minus b times x cubed. So I have that here. But I happen to know that b is negative 1, so this becomes c plus 1 equals 0. So c itself has to be negative 1, and that gives me c equal negative 1 here. Then I equate the coefficients of x. Now I did have an x term on the left, which was 1x, and then I have all of these on the right, which is c plus e minus b minus d. And I know that c is negative 1, and I know that b is negative 1, but I'm subtracting a negative 1, so that's a plus 1. So I have a negative 1 plus 1, so they knock each other out. So I basically get e minus d equal to 1. So that gives me an equation. And then the last one gives me another opportunity to find something. This last one is the constant, which is 3 on the left, and it becomes 1 minus c minus e on the right. But I know c is negative 1, so that becomes a 1. So I get 2 minus e. And then if I move the 2 over, I get that e is a negative 1. And then I can go back to this previous problem and I can figure out what d is, which turns out to be negative 2. Now, this is a long process. This doesn't happen instantly, right? This is a lot of heavy duty algebra here. So give yourself a break if you made some careless mistakes. In general, I would say textbooks try to keep the numbers relatively nice. So if you're getting really awful things, then you probably made a mistake somewhere. So then we're going to break it down. So we basically had our original rational expression and we decomposed it into these 3 simpler rational expressions. We're going to integrate each one separately. And then we're going to substitute in the values of a, b, c, and d. So you can see up here, if I can kind of get it all on the same screen at once, a is the value of 1. So this just gives me 1 over x minus 1 dx. And then b was a negative 1 and c was also negative 1. Now you'll notice that what I did was I split this integral into 2 separate integrals. So I have the negative x over x squared plus 1 and the negative 1 over x squared plus 1. I did the same thing for the d and e, which was negative 2x minus 1 over this x squared plus 1 quantity squared. I split it into 2 separate different integrals, 2 separate fractions. Now, why would I do that? What's the purpose for splitting it up? Well, I need to split it up in order to integrate it. Yeah, I know. You've done all this work. You feel like you've done enough. You should be done. You're not done. The whole point was to integrate, which you have not done yet, right? You just got to the point you could integrate, which is kind of nightmarish, but here we are. So how would you integrate this one? Well, you're going to let u be x minus 1, and this is going to become 1 over u du, which is the natural log of the absolute value of x minus 1. So this one is pretty straightforward. How about this second one right here, the first blue highlighted one? Well, I've got x squared plus 1 in the denominator. If I let that be u, du would be 2x, which is a multiple of the numerator. So I'm going to use just plain old u substitution on that one. So let me write down what these are going to become. So this one, basically, I let u be x minus 1, and I end up with 1 over u du as my integral, all right? Which gives me natural log of the absolute value of u. This one, I also do a u substitution. For this one, I have u equal to x squared plus 1. And so du is equal to 2x dx. And so when I do this one, I basically end up with, well, 1 over u again, all right? So my x dx, I'm going to have to solve for that. I can pull the negative out. I'm going to have a 1 half. So I'm going to have a negative 1 half out here. And then I'm going to get the integral of 1 over u du again, all right? So I'll be able to integrate that one after I'm done with that. Now, what about that third one, which is the second blue highlighted one? I can't do u substitution on this. It's not going to work because the derivative of the denominator is 2x, and I don't have an x in the numerator. So what I need for that is trig substitution again. I know you think I'm crazy. This is just a nightmare, right? So I need trig substitution. And this is going to be x equal 1 tangent of theta. And then I'm going to do trig substitution on that one, and that will lead to a result. Now, what about this third one, which is the first pink highlighted one? Well, it's more similar over here to this one, except we have something slightly different. On this one, when I do u substitution on it, I'm going to let u be equal to x squared plus 1. And then, oops, that's a u, not an x. Then my du is going to be 2x dx. And so I'm going to have minus the integral of du over u squared, which we can just integrate using the power rule. So that one's pretty straightforward. It's not too nightmarish. It's okay. What about this last one, this fifth one? Well, this fifth one is more like the third one. We're going to have to do trig substitution again. So this one is going to be trig sub again, and we're going to have basically the same substitution that we had on the third one, but it's going to be raised to a power. So again, we have 1 equal tangent, or x equal 1 tangent theta. And then we can integrate that, and we'll come up with a solution. Now, each one of these is going to take a fair amount of work. Some of them less than others, some of them more than others. The trig substitution definitely will take a little bit more effort. But when you're done and you scroll for pages and pages and pages, you should come up with something like this. Now, this isn't the only way that this can be written. Remember, when you have a 1 half at the front, it represents a square root. So you could actually have this under a square root. Because these natural logs are subtracted, you can move the square root in the denominator of the first argument. So there are things you could do to simplify it. You could split this into 2 fractions. There are some things you could do to simplify it a little bit or rewrite it in a different format. But this is the solution to that integration problem. It is doable, but it's certainly a lot of work. So I hope that you have enjoyed learning about the method of partial fraction decomposition and that it is making sense to you. In our next video, we'll be taking a look at other integration techniques. So there are some other integration techniques. Basically, this is a grab bag for, well, they're so specialized that what we're going to do is we're going to use a formula and apply the formula in order to integrate. So that will be in our next video, which is going to cover section 3.5. And I hope you'll join me there.